find the gradient field for the following potential function. So here we have phi of xyz is equal to z times the natural exponential raised to the minus xy. So we know that the gradient is defined by the operation of taking the partial derivatives. So we have to take the partial derivatives with respect to our three variables here. So we're going to start by finding all first order partials. So we have the partial derivative d phi dx. So this will be equal to z multiplied by minus y times the natural exponential raised to the minus xy. And we can just rewrite this as minus yz times the natural exponential raised to the minus xy. Taking the partial derivative of phi with respect to y, we have z multiplied by the derivative, which will be negative x, times the natural exponential raised to the minus xy, which leaves us with the beautiful final answer, minus xz times the natural exponential raised to the negative xy. And last but not least, we have the partial derivative of phi with respect to z. So this is just 1 times the natural exponential raised to the minus xy, or just the natural exponential raised to the minus xy. And the hard part is over. We're ready now to go ahead and find the gradient vector. So we can say therefore, or not the gradient vector, excuse me, the gradient field will be the vector f defined by the gradient of our function phi, whose components are these three partial derivatives. So we have the x component is minus yz times the natural exponential raised to the minus xy. Our y component is minus xz times the natural exponential raised to the minus xy. And our z component is the natural exponential raised to the minus xy. And there's nothing wrong with leaving it like this. If you want, you could take it one step further and factor out that the natural exponential raised to the negative xy multiplied by the vector minus yz minus xz 1. So either way, these are both beautiful forms for our final answer for the gradient field of our given potential function.